what we're finding, even when the analyzer is spot on in terms of calibration, when we put cameras onto the pipeline to actually see what's going on inside the pipeline, even though we know we've got dry gas, we've still got liquids running underneath. Now we've got sufficient evidence to say there's something desperately wrong in what we're doing, and we're beginning to, if you like, illustrate the problem to the industry. Particularly for a gas-fired power station buying millions of dollars a day, or an LNG plant buying millions and millions of dollars a day, small errors really make a big difference.
So how can that help the decision makers improve the plant performance?
You know, the midstream companies are saying, well, why are we spending millions of dollars pigging the lines and disposing of these? A lot of plants are at high risk of foaming.
What do you think the most exciting challenges and technologies coming through are going to be to help support the industry?
I think there's a lot of stuff going on.
Welcome to Pipeline Insider, your inside track through the mind-shaping gas processing. I'm your host, Jo Shales, and today we're kicking off our very first episode with a conversation that dives into the hidden side of gas. Have you ever wondered why some problems seem to appear out of nowhere? Why contamination can surprise even the most experienced operators? Or why hydrocarbon dewpoint measurements don't always tell the full story? That's exactly what we'll be exploring today. Our guest is Paul Stockwell, someone whose career started with a passion for understanding gas at its most invisible level, moisture and dew point. From pioneering new ways to measuring moisture in industrial gases to uncovering hidden operational challenges, Paul has spent years turning complex science into practical insights. In this conversation today, he shares what he's learned about the behaviours of gas you can't see, why small measurements can make a big difference in the real-world operations, and the lessons that anyone working with gas can take away. So let's get started. So, Paul, thank you for joining us. Can you tell us a little bit about how you got started in the world of instrumentation and gas measurement?
Yeah, certainly. I guess my first job was with an analyzer company that measured trace moisture, so moisture in industrial gases. And that is spread across the industry, really. Compressed air, specific gases like nitrogen, oxygen, argon, helium. And moisture content in all those gases is critical for a variety of reasons, but it gets you into lots and lots of different industries right across the board.
And so from that, you took the work and you created a foundation for doing your work in gas measurement monitoring. What
we did really was started specialising in natural gas, because apart from moisture, there's a number of other species that are really important. So hydrogen sulfide, H2S, is really important. So moisture dew point or water dew point, as well as hydrocarbon dew point. So it's quite a complex mix of analyses really that need to be correct for a variety of reasons really.
And when you were working and looking into all of this, where was your aha moment?
I guess my aha moment was I was sitting on a committee at National Physics Labs many years ago. This is pre-Google days, so I think it was Ask Jeeves or something like that. So anyway, somebody came into the meeting and said, I wonder if we can do something with tunable diode lasers. Never heard of them before. After the meeting, started digging around on what was then the internet. Lots of dead ends and cul-de-sacs and all sorts of things going on. But eventually found these three guys that are spinning out of the Jet Propulsion Lab in Pasadena. And JPL do all the research, a lot of the research for NASA. They were putting a TDL system onto a Mars polar lander mission. So I jumped on a plane and got across, had a chat with them, said basically natural gas is crying out for a better measurement. We've got this, and this. None of them are particularly great in natural gas. And they said, well, we'll possibly do stuff. So they had a look at it, and yes, we did. They produced a piece of kit which became the spectrosensors unit, and the forerunner really of all the TDL measurements that are now on the market.
And just for our listeners, can you just clarify what TDL stands for?
TDL is tunable diode laser.
Brilliant, thank you. And then as we go through this podcast, we're going to be going into a bit more technical insights into what Dewpoint is and measurement and monitoring. So could you explain to our listeners in a very simple way what Dewpoint is?
What Dewpoint is? That's a simple question, and a lot of people get it sort of strangely wrong. Yeah. So imagine if I had a Tupperware, I was going to say, but a plastic container on the desk, and I sealed it up and then put it in the fridge. So ambient temperature is what, 25 degrees C, something like that. We'd put it in the fridge and the temperature would drop to about 5 degrees, and we would see condensation. If we open that lid, we'd see condensation on the inside of the container. So what's happened is that air at a certain temperature is able to support a certain amount of water vapour in gas phase. By water vapour, it's the odourless, tasteless stuff. It's not steam that you see coming out of the kettle. It's what we breathe in. Air is at a certain temperature can hold a certain amount of water vapour. When we cool it down, it can no longer support the same amount. So you've actually, by cooling it down, you've not only hit the dew point, but you've gone past the dew point because we've got a film of condensation on the walls. But the important thing to remember at that point is that the gas space is still saturated. If we took that and put it into a freezer, obviously it would turn to frost or ice, but actually we'd see more drop out. So the gas space, whilst at +5, whilst we've got condensation there, the gas space is still saturated with regard to water vapour.
So why does it matter if it's saturated or not?
When we're talking about industrial gases that are increasing in pressure and decreasing pressure, then it really makes a difference. So if you pump your bike up with a bicycle pump, the pump gets hot because you're compressing a gas, and that's the same with these industrial compressors. That's fine, but if you cool it down, if you depressurize it, then the gas will cool down. And with natural gas, it cools down quite dramatically. So if you start with a wet gas, then you're going to end up with frost that will block regulators and valves and be quite dangerous.
And when you come across some of these issues with that dew point, can it just appear out of nowhere?
So long as you know what you've got, and that's the key. So with dew point, we've spoken about water dew point so far. In natural gas, there's also a hydrocarbon dew point. So with water, it's relatively simple. It's a single species, and you can draw a saturation curve. If you imagine a graph of pressure up the vertical scale and temperature along the horizontal scale, you can draw a nice smooth curve, which one side of the curve is saturated, and on the right side of the curve, it's dry gas. So if you know where you are, you can determine what's going to happen within the pipeline or within any system, really. And you can calculate what will happen at pressure. With hydrocarbon dew point, it's made up of multiple different species, and natural gas will go into dense phase, which means instead of this nice curve, which is quite logical with water vapour, you actually get it curls back on itself when it goes into dense phase. So the hydrocarbon dew point is a lot more complex. But your question about why is it important? Well, there's corrosion that can take place. If you've got liquid water in a pipeline, then it's more corrosive. If you're compressing the gas, then liquids don't compress and gases do. So if you're putting liquids into a compressor, it's quite a dangerous thing to do.
And you've talked very briefly there about the carryover and corrosion. And I'm assuming then foaming and condensation as well is all part of those outcomes of dew point.
Can be. Foaming is a little bit different in natural gas conditioning or natural gas processing. So natural gas has been underground for millions of years. It's got all sorts of things in there: sand, condensate, crude oil, all sorts of stuff, and that comes out when the gas comes out the ground. Then I don't know if you've ever been to a volcano. Have you?
I have.
Well, so you've smelt rotten eggs.
Yes.
Well, that's hydrogen sulfide.
Yeah.
So if you can smell it, it's fine. But round about, I think it's about 8 parts per million, it strips your nails out and you can't smell it anymore. A little bit more than that, you're unconscious. A little bit more than that, you're dead. It's quite a toxic component, really. So that's got to be taken out of natural gas before we can do anything with it. And the way they normally do that is with amine, liquid amine, that is in contact with the gas. That will remove both H2S and CO2 at different levels. But if the incoming gas has got liquids in there, mainly hydrocarbon liquids in there, that causes foaming in the processing.
And can you, with the carryover foaming condensate formation, are there any misconceptions around why they're generated?
Yeah. Well, one of the things we're now learning, having spent a career in Dewpoint, is that actually there's a lot of times when we actually get it wrong. So when we're measuring moisture level or hydrocarbon dew point, it's really important to know whether the gas is wet or whether it's dry. And so there's a number of different techniques we can use. Some are better than others, but they're all need to be calibrated quite regularly. Some are more stable than others, as I say, so they need to be calibrated less often than others. But they all need to be calibrated and make sure we get the right answer. Now, what we're finding is that even when the analyzer is spot on in terms of calibration, when we put cameras onto the pipeline to actually see what's going on inside the pipeline, even though we know we've got dry gas, we've still got liquids running underneath, which was a bit of you were talking about an aha moment.
Yeah.
That's another aha moment have we got this wrong? I mean, there's lots of industry standards. There's lots of instrument engineers working really hard on making sure, are we 1.5 or is it 1.35 or is it, and what we've seen is just a massive difference. So we can have a dew point of minus 40 degrees. Doesn't matter whether it's degrees C or Fahrenheit, it's the crossover, but minus 40. And the ambient temperature could be plus 25. So we've got a really good margin between the process temperature, if you like, the ambient temperature, and the dew point. We'd have to cool that gas by, what did I just say? 25, 40, 50, 65. Yeah. We'd have to cool it by 65 degrees C before we hit the dew point and we started to see condensate form. So you think every day of the week, that's dry gas. But then we put the camera in and we find actually there's liquid streaming at the bottom of the gas, streaming at the bottom of the pipeline.
And has that been a big surprise for people within the industry to understand that? Yeah,
it's been a big surprise to us. I mean, we didn't believe it at first. But when we first started seeing this, we thought, it can't be hydrocarbon liquid. It's got to be glycol, which is another one of those liquids they use in gas processing. Because otherwise, the analyzer would go into alarm because we've got liquids present, but they don't. Now we've got sufficient evidence to say there's something desperately wrong in what we're doing, and we're beginning to, if you like, illustrate the problem to the industry.
So with the realisation that what we've just been talking about, there have been quite a few surprises for people in the field. What do you think the top 2 or 3 things that operators or engineers or decision makers should be looking into but are often overlooked in the gas monitoring industry?
That's a good question. I think there's beginning to be a realisation that we don't have to just cope with the liquid carryover. So there's 2 sections to that. One is when it gets to the pipeline, operators are pigging pipelines and disposing of whatever comes out, and that costs quite a bit of money. It's more expensive to pig the line to get the liquids out than it is to prevent them getting in the first place. If we know liquids are there, then we can improve that separation system. And the same goes for further back in the process when we're looking at the gas coming into gas processing. So this is a known wet gas. It's just come out the gas wells. It's full of all sorts of contamination. But the front end filtration system on gas processing should remove the liquids and the solids from that. What we're finding is that if they're not removed, that increases the foaming and fouling within the gas processing plant. So again, what we're saying is if we can really get a handle on what liquids are carrying over and improve that phase separation system, then all the problems of foaming and fouling and adding defoamer and various other methods to sort of cope, if you like, with the liquid carryover come into play. And it's all about understanding how and when those liquids are getting into the systems that they shouldn't get into. And so the monitoring systems we have to date, until we came along with a process camera, we've now found are not sufficient. And people have, over the years, generated coping mechanisms. And what we're saying is, you don't need those coping mechanisms, just need to control what's going on.
And with that comes better measurement and observation.
Yeah.
So how can that help the decision makers improve the plant performance?
Oh, yeah. Well, from the pipeline perspective, first of all, the midstream companies are saying, well, why are we spending millions of dollars pigging the lines and disposing of these of the contents, really, when the liquids have come across from the suppliers? So they're looking at quite large operational cost reductions, both in terms of pigging, but also in terms of compressor servicing and stuff like that. And then if we go back to the gas processing plant, then a lot of plants are at high risk of foaming. The maximum flow rate they're able to operate at is lower than the design, quite often. If we can really improve that phase separation system by observing what's going on there and feeding that back into the phase separation process parameters, then we can optimize that process and really sort of help production, really, if you like, for that plant, and reduce OPEX quite significantly in terms of unscheduled outages and maintenance costs and stuff like that.
So if somebody was coming new into the industry or potentially taking a new role within a company, what could they be doing to make a real impact on the plant performance to make sure that they can get the correct measurements and be able to see the carryover coming through? Yeah,
have a look at the big numbers. What's really going to shift the needle for that particular company? So we're talking about liquid carryover specifically. Firstly, at the front end, if that can be improved, then we can decrease the maintenance costs, as we've said. At the back end, if the natural gas liquid process, the NGL recovery process as it's known, if that's not operating properly, then the company could be losing millions of dollars every year without knowing it. So by NGL recovery, basically what happens there is the gas is normally reduced in temperature to minus 20, minus 30 degrees C, something like that. The idea being that it goes below the dew point and then that knocks out that liquid. And then you've got a dry gas. But two things have to happen. One is you need to achieve that low temperature, and more importantly, you need to separate the liquids from the gas at that temperature. And what we're finding on the cameras, on the line view systems, is that more often than not, we're just hovering around the dew point. So that NGL recovery process has not really worked at all. We're spending the money on it, but it's not really removing much of the liquids.
So is there a simple mindset that these operators and engineers could be putting in place or thinking about to prevent those common issues in gas operations?
Yeah, put a line view in. It's the simple question. But no, we're looking at putting a line view in alongside flow meters and GC systems to validate the fact that the gas is dry. If you know it's dry, then you know the flow meter and the GC readings are correct. If you've got liquids in there, all bets are off. The flow meters could be reading anywhere between 2% and 20% overread, which is quite substantial if you bring it back to the fuel pump. Yeah. Particularly for a gas-fired power station buying millions of dollars a day, or an LNG plant buying millions and millions of dollars a day, small errors really make a big difference.
So with this measurement and observation that you're observing, how can this help decision makers make better decisions?
Well, one of the midstream companies has said, why are we pigging the lines and disposing of the products that are coming out? And they've gone back to their suppliers and said, you're sending us liquids. And the supplier said, no, we've got minus 40. It's not us, it's somebody else. So now we're putting cameras on the pipelines. They can say, no, it is you, and either you're sending it continuously on some occasions, or every now and again we see liquids come across. Then we can start working on optimizing the separation system that they've got.
Would you say there's any simple mindset that should be taken into account, or a simple mindset that those operators and engineers could be taking to make sure that they're asking potentially the right questions?
Yeah, it's probably a good question, because if it was a pressure measurement or a temperature measurement, then, okay, the sensor might be a little bit off. It's a pretty solid measurement, though. But when it comes to hydrocarbon dewpoint measurement, it depends how it's done. If you're actually measuring a dew point, then you know it's the right answer. But actually, when you're measuring the hydrocarbon dew point with a gas chromatograph, that's more of a guess. And let me explain what I mean by a guess. So a gas chromatograph will tell engineers the split of what's in the natural gas. So natural gas is normally about 95-97% methane or methane. Then comes ethane, propane, butane, and heavier hydrocarbons. And that will measure the split of what's in the gas and then calculate the BTU. So normally a gas chromatograph will measure up to C6. So methane is C1, ethane C2, and so on and so on. So a normal gas chromatograph will measure actually is up to C5, and then anything heavier than C6, it will lump into one number. And so those heavier ends are really, really small. It's usually 0.04% or something like that of the gas. It's really small. So in terms of BTU calculation, that's fine. But the problem comes when that one number is having to be split into umpteen higher levels or heavier level hydrocarbons. And it's not measured. It's just, they just know the number, the solid number. So they guess, basically, in a number of defined methods. There's 6 different defined methods. But it's basically a guess of what that split is. And how that the heavier ends are characterised is really, really important when it comes to hydrocarbon dew point. So depending on the method that you use, you can get about 100 degrees C split between the top and the bottom level. So you can go anywhere from -60 to +23, something like that, on depending on which method you use. So in terms of process engineers, they have to believe the number that the metering engineer gives them.
And are you seeing that demand from those engineers on requesting to have those split out more defined, or is it just that trend that everybody's used to, that you just have it all lumped into one?
Yeah, well, up until recently, everybody believed what was going on was absolutely true. And it's been validated in different equations of state, and that all works out in the lab. What we're finding, though, in the pipeline is very, very different to what's in the lab.
And from your perspective, where do you think gas measurement and monitoring is heading in the next 5 to 10 years?
I think there'll be more realistic in-pipe measurements. What we're finding is that the standards have been written around making sure that the gas analyzer makes a robust measurement. So normally the gas analyzer sits off of the pipeline somewhere, and there's a sample system that takes the gas from the pipeline, it depressurizes it, normally to around atmospheric pressure, filters it and puts it into the analyzer. So that the analyzer is in that happy place of its atmospheric pressure, it's clean, dry gas and whatever. And that's great for the analyzer because, speaking as an instrument engineer, the last thing you want to do is put liquids through an analyzer. So that's why the standards are written that way. API 14.1, there's an ISO equivalent 10715, I think, that all dictate how that sample system should handle the gas. But of course, if you've got the wrong hydrocarbon dew point, you've actually got wet gas in the pipeline, but it's telling you it's dry, and it's not helped by filtering out any liquids that might be in the gas because you're not counting them then. So the BTU will be wrong, as I say, and if you're relying on a GC to tell you the hydrocarbon dew point is right or wrong, then that's probably not a good way to go. Let me give you an example. Okay. Bear with.
I like examples. Go for it.
So, when it's snowing, the snowflake's falling, and as it falls, it's actually pulling water vapor out the air to form the snowflake. And the snowflake, as it falls, gets bigger and bigger and bigger, and more water vapor comes out. So actually the gas space, when it's snowing, is getting drier. Even though you've got all the snow coming down, the gas space is drier. And we think that's what's happening in a pipeline. When you've got cooling or heating or whatever going on. We saw an episode where we had a stoppage for 2 days in the pipeline. They didn't depressurize, it was just the gas had stopped for 2 days. And at the beginning of the 2 days, we saw a nice dry pipeline. At the end of the 2 days, somewhere along that line, the pipeline temperature or the pipe temperature got cooler than the dew point, and so we saw a lot of condensation on the pipe wall. If we measured the gas at 2 days ago before the stoppage, we'd have one answer. If we measured the gas again after all that condensation had fallen out, we get a dry gas. So even though you've got liquids in the gas, you've got dry gas. And it's a difficult concept for some people to sort of understand, but surely if it's wet, it's wet. No.
And from your experience and from what you kind of predict is going to happen in the future, what do you think the most exciting challenges and technologies coming through are going to be to help support the industry?
I think there's a lot of stuff going on in the optical space. So spectroscopy is quite exciting. There's several different types of spectroscopy, Raman and absorption, and also fluorescence as well. And I think that as we move forward, it's going to come to the fore and be more and more useful, really.
And is that the area that you would advise anybody in the next generation of engineers and operators to focus their career on?
Yeah, if you're into measuring stuff, which I am, then yeah, I think optical is the way to go for a number of different reasons. Either the identity of the gas or the quantity of what we're looking at in trace levels. It's usually quite a fast-moving industry in terms of photonics. So by photonics, I mean the optical components that are becoming available and on the market at a reasonable cost. TDLs are a good example. When we first started looking at TDLs, they were the size of the truck and they operated at liquid nitrogen temperatures. Now they operate at ambient temperatures as little tiny diode. It makes it so much easier.
And just the final question before we wrap up is, from today's conversation, what would be the main thing you want your listeners to take away with them? Question
hydrocarbon dew point, I think, is the overall thing that we've learnt is, no, you don't know if the gas is wet or dry just by measuring the hydrocarbon dew point. Take a look inside the pipeline.
And if our listeners want to learn a bit more about you and your work, where do they go?
Connect with me on LinkedIn is probably easier.
Brilliant. Thank you very much.
Okay. Thank you.
That wraps up our first episode of Pipeline Insider. Thank you, Paul, for all your valuable insights into gas behaviour, dewpoint measurement, and the small details that make a big difference in operations. We hope today's conversation gave you a fresh perspective on the challenges and innovations shaping gas processing. If you enjoyed this episode, be sure to subscribe so you don't miss future conversations with industry leaders, innovators, and the people who keep the pipelines running safely and efficiently. Thanks for listening, and we'll see you next time on Pipeline Insider.